Hello everyone, welcome to heating effect of current. And first, before we move on to the verifications, let's talk about the theories on why, a circuit or the wire of the current passing through the conductor heats up. Now here, there are basically two theories. And also, the heating effect of current, when current is passed through the conductor, heat is produced, which is known as heating effect of current, or it's also known as Joule's heating effect as well. The scientist Joule discovered it first. Now, for the first theory, it is a collision theory. So, what this says is when a battery is connected, a potential difference, an electric field is produced, and then the free electrons in the conductor they gain kinetic energy due to the electric field and then of course of the electric force, and thus the electrons start to move and start to accelerate. And when the electrons do move forward, they have a chance to collide with each other, and thus they lose some kinetic energy, which is then converted into the heat. So basically, the collisions that the electrons experience, they lose the kinetic energy, which is converted into heat. And for the second part, we have the current and resistance theory. So here, as you know, in a circuit there is some resistance, and here a current is passed through it. Here, even after the resistance, the current passes through the little bit of resistance here and then keeps on flowing. So that means that the resistance opposes the flow of current, and if the current still wants to flow past the resistance, that means some work must be done to keep the current flowing even if there is an opposing force of a resistance. So that means the work done to keep the current flowing is converted into the heat. Or the work done is converts into the heat of the circuit. Now these are the two theories, and here, according to Joule's experiment, what he found that was heat was directly proportional to the square of the current, and directly proportional to the resistance, and directly proportional to the time taken. And here, combining all of this, we get H directly proportional to I square RT, where H is equals to I square RT. Now here, this is in fact for the for the SI system. The SI system. So this is for the SI unit. And here for CGS system, the heat produced is equals to I square RT by J. And this J is equals to 4.2 joule per calorie, which is known as Joule's mechanical work or mechanical equivalence of heat. Now here we can also do a derivation of the heat produced. Now we know that the potential difference is equals to the current into resistance, and also that current in itself is equals to charge by time, or charge is equals to current into time. Now we don't put I equal Q by T here because in the heat equation we don't have charge. But what we do need is work done. The work done in the circuit is equals to the potential difference into the the charge, because potential difference definition is equals to the work done per unit charge. And here we can simply put IR into IT, therefore heat, because work done is heat, is equal to I square RT. This is the derivation. Now time for the verification. Here we have a calorimeter with a stirrer. This the thermometer which measures temperature T, voltmeter, ammeter, and this whole thing is the calorimeter, and this is insulated. And we have a resistance R here, and we simply have this water up to this level temperature here because we pass through current, and of course there is heat produced, and the heat produced directly affects the water, and it is much easier to measure the temperature of liquid of water instead of just air. Now first we need to prove that the heat is proportional to I square. Now first what you do or what they did in the experiment was they measured the temperature, which let's say was theta 1, and after some time the current was heated, the current produced some heat, and the temperature rose to theta 2. Therefore, we have a change in temperature, which is theta 2 minus theta 1. Now we can use the heat equation of ms d theta, and here what the experiment due to the experiment it was found that, well, let's say this is heat 1 and this is change in temperature 1. So the first heat by, let's say, the first current passed was equals to the next heat, that means a different change in temperature to the different current applied, and so on, like this. Well, what this shows is that the heat is directly proportional to the current square. So if we plot a graph between, well, I squared and heat, we get a straight line. Now similarly, you can just see these same points here and here, but here what I'm going to tell is that, well, they found the ratio of the first heat to the first resistance. Oh, I forgot to mention, in the first part, they kept the resistance and, well, time constant. That means they took a certain amount of time and a certain amount of resistance but passed through different amount of current each time. And here the current and time are kept constant. And what they found when they changed the resistance is that the heat by the resistance was equal to H2 R2, or the different heat by the different resistance, and so on and so on. So this proves heat is proportional to resistance, and we have the same graph giving H and R. And of course we have kept current and resistance the same, and we still get heat by temperature is equal to the different heat by the different time taken, thus proving heat is directly proportional to time taken. And of course we again have the heat time graph as a straight line. So overall this proves that heat is directly proportional to the square of the current, the resistance, and the time taken. And then we have for CGS I square RT by J CGS, and H is equals to I square RT in SI system. So this is for heating effect of current. If you learned something new, please like and subscribe. Thank you.